Okay, folks, I'm going to run through 4 examples here. Example A and example B are going to be examples of u-substitutions that work out perfectly. Sometimes I'll call them a perfect substitution, whereas example C and examples D will be differing by a constant, and so there's going to be something a little bit trickier with those. So I'm actually going to work A and C together, and then we'll work B and D together. So here we go. So I'm looking at this particular integral. We've got 3x squared e to the x cubed dx, and that's not an elementary derivative rule. I don't know what function, when I take its derivative, gives me that expression. It's not one that I've memorized. And I can't use the power rule on it, so I think I'm going to have to try one of my techniques of integration, and at this point we only have the technique of u-substitution. So I think this is geared up for a u-substitution. How come? Because I see a function in here, namely x cubed, and I also see the derivative of x cubed. That derivative exists up to a constant. So that's going to give me a hint that I should try a u-substitution on this. Here we go. I'm going to go ahead and say, let's let u equal x cubed. Now I need to immediately differentiate, so it gives me du dx is equal to 3x squared, or du is equal to 3x squared dx. Going forward, folks, I'll usually jump from this step down to this step in a single step and not do this secondary step. Okay? So now I'm ready to do the u-substitution, so I'm going to say that our original integral is equal to the integral of, so in place of x cubed here, I'm going to put a u, so this is going to be e to the u. And then let's look at this. In place of the 3x squared and the differential x, there's 3x squared differential x, I'm going to replace that product with du. So over here I'm going to put in our du. Okay. Again, that's a substitution step, and sometimes it might be helpful to remind yourself that between 3x squared and e to the x cubed, I've got multiplication, and in fact, if one way of thinking about it is in between e to the x cubed and differential x, I also have multiplication. So this is really just 3 factors multiplied together. So in place of these 2 factors, I'm replacing it with du. Okay. So let's compare and contrast these 2 problems. I'm going to clean this up just a little bit so we can see it better. This one is a little bit harder on the eyes to look at than this one. I feel more comfortable taking the antiderivative of this than I did up here. So here we go. This gives us, what is the antiderivative of e to the u? Well, it's just e to the u plus c. This part always makes me sound like I've got bad English because I say, well, u wasn't the variable we were asked to solve for, was it? Well, no. Well, what was u? Well, u was, in this case, x cubed. So I simply, the phrase is I back substitute what u was holding the place of, and I get e to the x cubed plus c. Okay? So that's my final answer. Folks, I highly encourage you to now take the derivative of this and confirm that you get what was in the integrand. So in your own time, go ahead and take d dx of e to the x cubed plus c and show that you get the integrand. Okay, now let's look at C over here. So C is an example of something that I call an imperfect u-substitution. Let's see what happens. I look in here and I see an expression, in this case x cubed, and I see the derivative of that expression up to but not necessarily including its constant. So the derivative of x cubed is 3x squared. I don't see the 3, but I've got an x squared part. That tells me I probably want to do a u-substitution. So here we go. We're going to let u be the expression whose derivative also shows up. So then we say that du is equal to 3x squared dx. Notice that, like over here, as I said, I didn't write the du dx step. You're welcome to write this a few times until you get comfortable with it. Eventually people just jump to this statement here. Okay. Now, just like before, I'm looking up and I'm wanting to do some sort of substitution like I did over here. I look up and I see, okay, I've got a dx, great, I've got a dx, and I've got an x squared factor, but I don't have a factor of 3. So the way I choose to do a u-substitution is this, and everyone does them a little bit differently. I'm going to go ahead and divide over that unnecessary factor over to the other side. So that gives me 1/3 du is equal to x squared dx. Because now what I have on the right-hand side aligns exactly with factors that I already have under the integrand. So now I can actually do the substitution. So here we go. We're going to say that this integral is equivalent to this integral here, which is the integral of, now, in place of the x cubed, I'm going to place a u. So this gives me e to the u. Okay. And then in place of the x squared dx, I'm going to replace it with 1/3 du, which I could write right here like this. Or in this first example, I'll go a little more slowly. I could write as 1/3 e to the u du. That's how you would expect to see an integral problem. But of course, what could I do? I could pull that constant out of the integral, and we get this expression. Okay? So again, in my opinion, this expression is easier on the eyes than this expression. It's easier to determine what function would have e to the u as its derivative than it would be to determine this function here. Again, these u-substitution techniques, though, are just techniques. They're just meant to make your lives easier. Okay? So out we can actually take the antiderivative, and we end up with e to the u plus c. But again, u wasn't the variable you were asked to solve for. What was it? What u was x cubed. So you get 1/3 e x cubed plus c. Okay? Folks, pay attention to the similarities and differences across A and C. In both cases, we did the same procedure, but C had this extra step right here. After I wrote what du was, I looked up and realized, well, I'm off by a constant, so I adjusted the constant of the u substitution. Okay? I didn't have to do that in part A, because here, A was what I called a perfect substitution. We had a constant of 3. We already had a constant of 3. All right, in the next video, we'll work the next two.